Good morning. Cool to have you here. Yes, so next Monday, let's talk about what's going to happen next Monday. That's the focus here. Next Monday, we will not look at problem set 4, do seminar, quiz 4, etc. But what we'll do is we'll take the first midterm exam, and it's basically over problem sets 1, 2, and 3, which is chapters 12, 13, and 14. So chapter 12 was thermodynamics. We talked about entropy, Gibbs free energy, how that works with enthalpy, jazz like that. Chapter 13 was equilibrium, talking about values of K, what it means, how to calculate them, K and KAs, KBs, those kind of things came in chapter 14, which was the acid-base part. We also talked about buffers and jazz like that. Everybody in this room has taken a midterm from me before, and it will be identical. All right, 12 multiple choice questions, 4 short answer questions. You've got about 90 minutes to complete it. There's an integrity statement on the front page I want you to sign. Should be pretty mellow. So what we're going to do today, Friday, and possibly Monday is just go over some sample problems, all right? And I'll give you a chance to work on them yourself, which I encourage you to do. We'll then talk about the answers so you can see how your knowledge base is, jazz like that. On Monday at 1:10, in addition to taking the midterm, you'll also turn in Exam Prep 1 worksheet. The exam prep is single page, double-sided, some questions followed by the answer, show detailed steps how you go from the question to the answer. And if you get stuck on any of those, man, reach out to me, all right, or the tutoring center or your friends or whatever. But I want everybody to have those skill sets before you take the midterm, all right? So I'm trying to help you get prepared. You'll also turn in the acid-base titrations lab that we did on Monday. We'll also go next door and do a lab which is really similar to what we did on Monday, but it's the titration of a weak acid lab. I'm basically going to give you a weak acid, and I want you to characterize it using titrations. And there's actually a lot of cool stuff you can do. You can find the molar mass, and you can find the Ka, and you can find concentrations and stuff like that, which for a chemist is pretty cool. So it's basically just what we did on Monday, just repurposed a little bit. Should be pretty chill. Questions? Any of that kind of stuff. Reed did just find a typo in the acid-base titrations lab, which I apologize. There's one of the post-lab questions that says, look in problem set 2, that should say problem set 3. So again, my apologies. In the old days, it was problem set 2. Now it's problem set 3, and I didn't update, so my bad. Sorry about that. Questions on it? So without further ado, let's get into this. Check it out. If you have questions on anything, of course, you always know you can reach out to me. So we're going to start off with some stuff from chapter 12. This is an entropy question. This problem has carbon tetrachloride reacting with oxygen. It makes carbon dioxide and some chlorines. And I'd like you to find the standard entropy change for this reaction. Now, this reaction will be an entropy of products minus entropy of reactants. You can look at the values right there. Entropy values are always greater than 0. They could be 0 if it's that pure crystal at 0 Kelvin, but that's like never. But they won't be negative, that's for sure. So see if you can find which of those values corresponds to the delta S for this reaction. We'll talk about it in a little bit. So on a problem like this, you want to take the sum of all the delta S of the products, and you want to subtract from that the sum of all the delta S of the reactants. And you can use these values right here. All entropy values will be greater than 0, in our case anyway. The only other thing I can think about, chlorine has a 2 right there. So when you do the chlorine part, you want to multiply this number by 2. But anyway, if you got 240.44, answer C, you are good to go. Here you can see down here, I plugged the values in. So this is CO2, this is chlorine. I multiplied it by 2. You subtract the CCl4, you subtract the oxygen. Entropy is positive, so this is an entropy favored reaction. When delta S is greater than 0, entropy gives it a thumbs up. Sometimes entropies, though, can be negative. Those are just reactions that entropy doesn't like. So, any questions? Excellent. Here's a reaction, very similar to what we just did, but this is for delta G, Gibbs free energy. It's also a Gibbs free energy reaction. So you'll take the sum of all the Gibbs free energies of the products and subtract the Gibbs free energies of all of the reactants. One value is missing. So we'll talk about that here in a little bit, but let's see if you can figure out what the answer for this is, and we'll talk about it here in a little bit. Okay, when you don't have delta H and delta S values for a reaction, finding delta G from individual values is another way to calculate if it's going to be spontaneous or non-spontaneous. It's usually not as good as going with delta H minus T delta S, but it is pretty cool, so better than nothing. So in this value, we don't have delta H and delta S apparently, but we do have all these values. But notice, of course, that we have CO2, methane, and water. Methane is CH4. We don't have oxygen. And the reason I wanted to put this out here is because the enthalpy and Gibbs free energy for the elements in their pure states equal to 0. So most of the time, if you don't have a value, it just means that it's 0, and that's the case here for oxygen. So what we'll do here, products delta G's minus reactant delta G's, we'll ignore the two O2s because oxygen's normal state is a gas. We will multiply the water through by 2 because of that 2 right there, products minus reactants. If you got answer E, you are good to go. So down here you can see here's products minus reactants, CO2 and 2 waters. Here's the CH4, 2 times oxygen is 2 times 0. Comes out to be a negative 800.8 kilojoules per mole. This is a spontaneous reaction. Delta G is kind of the ultimate thumbs up or thumbs down for a reaction. And if you get a negative delta G, that's like saying you have a positive delta S of the universe. These are the reactions which are going to occur. Thermodynamics says, yes, this reaction, I want it to go. If it would have been a positive delta G, chemists would refer to it as non-spontaneous. Those reactions typically don't occur by themselves. So, any questions? All right, here's a reaction where we do have delta H and delta S, and you want to calculate what the delta G value. Again, this is usually the better way to calculate delta G, but again, you can do products minus reactants. Anyway, see if you can figure out what the value of delta G is. Watch the units of delta H and delta S. They must be the same before you combine them. See what we can do with this. Okay, so this is the so-called Gibbs equation, delta G equals delta H minus T delta S. And you can see the effects of both enthalpy delta H and entropy delta S on the Gibbs free energy value. Remember, delta G is the ultimate will it occur, will it not occur kind of value. And you can see then the contributions of these to what's happening. Now, if you want a delta G to be negative, which is spontaneous, the thumbs up, then you want to have a negative delta H and a positive delta S. Now, negative delta H will make delta G negative, right? If this is more negative, this becomes more negative. But this is like a subtraction addition part right here. And if you have a positive delta S times negative T makes this whole term negative. So when entropy is negative, like we have right here, a negative delta S times a negative T makes it all positive. So entropy here is telling the chemist that it doesn't want this reaction to go, all right? It's not happy. And you can understand that because you've got a gas going to a solid. Gases always have more entropy than solids and liquids. So entropy says, whoa, this reaction is lame because I'd rather have more gases on this side and less gases on this side. But enthalpy, on the other hand, says, heck yeah, let's let this go. Very big and negative makes delta G want to be negative. So when it all comes down, you just got to plug these values in. Now, delta H is usually in kilojoules, while S is usually in joules. And you've got to use kilojoules and kilojoules or joules and joules, and it doesn't matter. What I usually do is I turn delta S to kilojoules. If you go over 3 spots, that will make it a kilojoule value. So minus 0.10836 would be the kilojoules per Kelvin reaction, blah, blah, blah. But any way you want to do this is fantastic. But if you throw this all in and you got answer B, the negative 568.9 kilojoules per mole, well done. So this reaction is spontaneous, negative delta G. It's spontaneous because this reaction is enthalpy favored. It's a negative delta H. This reaction is not entropy driven. Entropy is a negative number. It doesn't want this reaction to go. So enthalpy and entropy are fighting, but enthalpy is a lot more powerful. In this particular example, in entropy, it overpowers it, makes delta G look like delta H, basically. Questions on any of that? All right. So here's a reaction which, instead of numbers, it talks about what the impact is of the different signs of delta S and delta H. So here we have a reaction. It's a positive delta H and it's a positive delta S. And we'd like to know something about delta G, the spontaneity of this reaction. So see if you can use this information and this equation, of course, to figure out which of those 4 expressions there is correct. We'll talk about it here in a little bit. Excellent. Let's talk real fast about these terms and kind of how they all fall together. We talked a little bit about delta G already, how if delta G is negative, those are the reactions that occur. Thumbs up in your instructor's world, which is silly, I know. Anyway, thumbs up means negative delta G values, all right? It doesn't matter if it's -5 or -5,000. As long as it's negative, it should be spontaneous. So when I say something about spontaneity or spontaneous, that means that delta G is negative. It's going to occur. Now, we can introduce, though, the idea of equilibrium as well, because product-favored Ks have values much greater than 1. So you have a lot more product than you have a lot than reactant. So product-favored also is a way to imply spontaneity. It's product-favored means that your delta Gs are going to be negative. So negative delta G, K is greater than 1, same thing. Likewise, a positive delta G would be non-spontaneous. And likewise, that would imply a reactant-favored K, and Ks that are reactant-favored are less than 1. So all of those weak acids and weak bases that are out there, they're all Ks less than 1. They would be, in chemists' world, non-spontaneous. They don't really happen that much. Maybe 1 in 10,000 reacts, but by far, most of them stay as reactants. So in this problem, then, you've got a positive delta H and a positive delta S. Now, if delta H and delta S are the same sign, you're going to have a big time dependence on temperature. In the last problem, we talked about when delta H and delta S were both negative. And at that temperature, delta H overpowered delta S to make delta G negative. In this case, it's kind of like flipped. You got positive delta H and positive delta S. Now, a positive delta H does not want delta G to be negative. Like positive numbers don't want to be negative. It sounds a little weird, but that's the idea. So this is that a positive delta H would be not enthalpy favored. That's all the endothermic reactions we've talked about. However, a positive delta S, entropy when it's positive, it loves to make reactions happen. Because positive delta S times negative T makes all of this negative, and negative all of that makes delta G want to be negative, all right? So in this problem, this is an entropy-favored reaction, and delta S is positive. But this endothermic delta H, a positive delta H, that's not an enthalpy-favored reaction, all right? So you've got the classic fight here of entropy versus enthalpy. Which will win? Sound effects not necessary. I saw a Mortal Kombat trailer this morning, so I think I'm a little okay, prop that back on. Questions on anything except Mortal Kombat, because I really don't know that much about it. Come over here. Okay. Wow, I'm in a weird mood this morning. Sorry. Anyway, back to your regular syllabus programming. So we got to figure out here when delta G is going to be negative, all right? Because if delta H is positive, it is quite possible that delta G would be positive as well. Delta H is usually a powerhouse. However, if entropy times temperature can overpower delta H, then this term would make delta G more negative, all right? So this reaction absolutely could be spontaneous product favored. It won't be at all temperatures, all right? Because usually delta H is a lot bigger than delta S, and it will overpower entropy. However, if the temperature gets high enough, which is answer B, then you're going to have a spontaneous reaction. So higher temperatures will have spontaneous reaction, i.e. higher temperatures, bigger T, and negative T times delta S. This part will be more negative than delta H is positive, making delta G negative, making it spontaneous and product favored. Now, high and low temperatures is very vague, all right? It's just that there's going to be some threshold temperature, which we'll talk about in a little bit, where the delta H isn't able to overpower delta S anymore. And at those higher temperatures, that's when delta G is going to be negative. Okay. A lot of silliness in there, especially with the Mortal Kombat. Sorry about, don't know where that came from. Questions on any of this jazz? So this reaction kind of adds up a lot of the things we've been doing to calculate delta G. But in this problem now, you have individual delta H's, you have individual delta S's. So you first want to find delta H of the reaction and delta S of the reaction. Then you can combine both of those in the Gibbs reaction to see what the value of delta G is going to be. Again, note that O2 here is an element in its standard states, so delta H will be 0. Delta G would also be 0 if you had it. Anyway, see if you can calculate delta H, then delta S, and then finally delta G to make it match with one of these. We'll talk about it here. So on this problem, what you want to do, you want to find like delta H first. That would be delta H products, these two, minus delta H reactants. You don't have to worry about O2. It's an element in its standard state. Then you'll have a value for delta H. Then find delta S, products minus reactants. Now remember, all entropy values should be positive, so you do have to worry about the elements in their standard states. It's only delta H and delta G that you don't have to worry about it. So then you've got delta H, you've got delta S, combine them to find delta G in the Gibbs equation, turn Celsius to Kelvin. Remember that delta S is usually in joules, while delta H is usually kilojoules. So you want to divide delta S by 1,000 to get a kilojoules, or multiply delta H by 1,000 to get joules, whatever you want to do. But if you did all that and you got answer D, pat yourself on the back. So here's a lot of math, all right. Basically, it's delta H products minus reactants. Here's the oxygen, which is 0. I got an exothermic delta H, a negative delta H. Here's the same problem with entropy, products minus reactants. Again, the oxygen does have a value, so you want to make sure you plug it in. Positive 125.7, this is an entropy favored reaction. If you have an enthalpy favored and an entropy favored, delta G has to be negative. That's the only answer you're going to get. And so when you do all the math, remember to put delta S in kilojoules, making them both the same kind of unit, negative 233.5 kilojoules per mole. This reaction will be spontaneous at all temperatures because delta H is negative and delta S is positive. If they're both the same sign, like both negative or both positive, that's when you're going to have to worry about the temperature, all right? But in this case, if this is negative and this is positive, delta G negative, all temperatures. If this was positive and this was negative, delta G would be positive at all temperatures, and you wouldn't be able to make it spontaneous. Any questions on that? Cool. These problems are tedious, but they're not hard, just, step by step and stuff, so. All right. Now, this question has a negative delta H and a negative delta S. So remember, if the signs of those are the same, both negative or both positive, temperature is going to be a player, all right? So Daria and I want to do this reaction, and we want to know at what temperature this becomes non-spontaneous, when it's not going to occur. If we're going to do this reaction to make something, to make money, we want delta G to be a negative number, all right? And with these two being negative, at some temperature, entropy is going to be able to overpower enthalpy and make it non-spontaneous. So we want to make sure that we're always at a spontaneous, i.e. a negative delta G, not a non-spontaneous positive delta G temperature. So what I would do in this problem, let delta G equals 0. 0 equals delta H minus T delta S. And if you solve for temperature, you're going to get one of these numbers. Think about if it's Celsius or Kelvin. We'll talk about it here in a little bit. Okay, so when delta H and delta S have the same sign, temperature becomes a factor. And sometimes it's cool, like in this problem, to find the threshold temperature where it either goes spontaneous to non-spontaneous, which is what we're dealing with here, or the opposite from non-spontaneous to spontaneous. So what you want to do is just let your delta G equals 0. And if you do that, then 0 equals delta H minus T delta S. Well, if you add T delta S to both sides, then you get T delta S equals delta H. And you want to figure out temperature, so you will divide both sides by delta S so they cancel. So the temperature will equal delta H over delta S. Now, like before, delta H usually in kilojoules, delta S usually in joules. So convert one over to the other. Again, what I would do is probably go delta S. I would move it over 3 spots, so 0.0126. Notice you've got a negative over a negative. Temperature in Kelvin anyway must be positive. So that's why this only applies if the signs of both of them are the same. But if you do that, it comes out to be 7,620 Kelvin, which is a crazy temperature. In Celsius, this would be 7,350. So as long as Daria, I think I said, and I were doing this reaction under this temperature, we'll end up with a negative delta G and get our stuff out. So, woohoo! Anyway, so if you went to a temperature above 7620, then the entropy disfavored part would overpower the enthalpy favored part. And that's when you'd start getting positive delta G's. But as long as we would do this under this temperature, then the negative enthalpy favored value for delta H would overpower the entropy part, and it would still give you a negative delta G. Any questions on that? If the signs aren't the same, if delta H and delta S are opposite, then you can have the always spontaneous, always non-spontaneous. Negative delta H and positive delta S, i.e. enthalpy favored and entropy favored, that's when you're going to have the always spontaneous values. On the other hand, if it's the opposite, if it's a positive delta H and a positive, if it's a positive delta H and a negative delta S, there we go. That's neither enthalpy nor entropy favored. That's going to be the always non-spontaneous values. Is that cool? Okay. This is an extension of equilibrium constants to delta G. And at the very end of the equilibrium chapter, this was one of the things we did. You can calculate delta G directly from K values. So in this one, we have a KSP. This is what we did in lab for KSPs. We're going to do more with KSPs here coming up. Don't worry about that. This is the value of K. Delta G equals minus RT natural log of K. See if you can figure out what the value of delta G is going to be. Okay, we've seen a lot of equilibrium constants so far. We've seen Kas and Kbs, we saw Kcs and Kps, and we'll see some more coming up too, I won't lie. But anyway, this is an awesome way to go straight from an equilibrium constant to a Gibbs free energy value. So instead of doing delta H minus T delta S or something like that, equilibrium constants direct to delta Gs are pretty cool. Now, remember in the back of your mind what we talked about over here. Negative delta Gs correspond to Ks greater than 1. And positive delta Gs correspond to Ks less than 1. And our K, KSP, you can ignore what kind of K it is. K is certainly less than 1. So if K is less than 1, we had better get a positive delta G here, or else something will be a little weird. So in this problem, you want to go delta G equals minus RT natural log of K. Make sure you use natural log. Don't use base 10 log, the LOG, which is what we use with pH all the time. You want to make sure you use natural log. T is the Kelvin temperature, so Celsius to Kelvin would be 298. R is the energy R. It's 8.3145 joules per mole Kelvin. But anyway, plug all that together. The number comes out to be pretty big, but that's in joules per mole. So if you divide by 1,000, you'll get 34.8 kilojoules per mole, which is perfect for that answer right there. So, and again, checking yourself, K less than 1, delta G positive. All right, if K would have been greater than 1, we should have gotten then a negative delta G right there. So. Any questions on any of that? Cool. So for example, like on the acetic acid lab on Monday, you found a Ka. Ooh, you want to know what the delta G is? No problem. Minus RT natural log of K. And that would tell you what the value. And your K would be less than 1 for acetic acid, so your delta G should be a positive number as well. So as a chemist, this is cool. All right, so questions? I'm going to wait to do the next question until Friday. I think that kind of makes sense. I don't have a lot of time left. So I think that's it for today. I appreciate you being here. We'll do more review for the midterm on Friday. Have a great day.